I suggest we start. We start the last lecture before Christmas. And we start a new part today. So last lecture we finished the part on equality constraint optimization, which was, let's say, the easy part of constraint optimization, or the easier part. But we already digged into several details, and some of these details were the idea that you can introduce a merit function in order to ensure that you can make progress. And there was another topic that was regarding the possibility that you might get negative curvature in your Hessian updates, and then what to do with it. And there we very briefly mentioned this notion of damped BFGS updates, which can help you in this case. So these are all features that are used in existing algorithms. We will not program them all, because it's just too many things for this course. But I wanted you to know about them. What we will do today is derive the first order necessary optimality conditions for inequality constraint optimization, actually for the most general case. And it will culminate in what we call the so-called KKT of optimality conditions that are due to some people, Karush, Kuhn, and Tucker, that developed Karush independently from the other two. These conditions in the 1930s and 1950s. So Karush was much earlier, it seemed, all living in America. These KKT conditions is what we want to end with today. But I want to really make the connection between everything we did until now. And so in order to start, let me just give the setting. So the setting is, as you might guess, the general optimization problem. But let me first start to say where we are. We are now in part 4. And we are in chapter 13. And this is about inequality. Constraint optimality conditions. And the setting, as I said, is the task to minimize a scalar function f of x in some space R of n, where we have constraints which can be either equalities or inequalities, denoted by h. That's the optimization problem we want to look at. F is scalar, of course. G is a function from Rn to Rm. So we keep that notation, and H is a function from Rn to Rq. So I use the index Q here. Please, it should not be confused with the index for the Lagrange dual function that we, with the name for that we used at some point. But I think we are sufficiently far from it to avoid confusion. Yeah, and of course you remember what was the Lagrangian. The Lagrangian of this problem, just for exercise, will be something that depends on three quantities, namely x and lambda and mu. And it will be given by this expression, lambda transpose g minus mu transpose h. And what we want to do is we want to derive optimality conditions. And in order to do so, we will have to go through the same analysis of the geometry of the feasible set that we did before for equalities. And things are a little bit different here. But let me just start with recalling what is our feasible set. It's a set of all points which satisfy all the constraints. It's nothing else. But what we can now define, and we use exactly the same definitions that we did before, we can define a tangent vector. Yeah? I will not write down this definition again onto the blackboard, but the tangent vector is actually the derivative of a curve that's completely in the feasible set and emanates from a point, at some point at x star. So that's something you should be aware of. It's something tangent vector at x star, element in omega. So you take a point from the set, and then you can define a tangent vector, and you can test if some vectors are tangent vectors or not by a relatively theoretical definition that we gave last time. And then you can collect all possible tangent vectors, and then you get what we call the tangent cone. So I will also make this brief. And this tangent cone is actually denoted by t of omega at some point x, or x star maybe. And that is then the collection of all tangent vectors that are emanating from one set. This is slightly different for equality than for inequality constraint optimization, but the definitions are the same because they used only the set omega and they said the curve should be completely in the set omega. I would like to directly come to the flash, so to say, the part which is important here. You remember that in equality constraint optimization, we said the tangent cone is an abstract object, while a much nicer object to deal with would be the feasible cone, right? The linearized feasible cone. And the linearized feasible cone is defined as before, but no, actually it's not true. I will define it a bit later because I need some definitions in between. I just want to recall one condition which is using the tangent cone. It's also just something that we call a theorem. I think we called it variant 1 or something like this. And that said that if x star is a local minimizer, then first of all x star must be element in omega. That was clear, it must be a feasible point. But second, also for all p that are element in the tangent cone at x star, for all these directions in which you can actually move freely, allowed directions, you must have that p transpose nabla f at x star is an upwards direction. And the proof is as simple as before. It's just this a recall of a theorem, but it's still valid before. But this is not computational, right? So it's just a statement. What is necessarily true when we have an optimizer? Every tangent direction must go uphill. That's it. But then this thing needs to be characterized, and it will be a bit different for equalities than for inequalities. And in order to go on, I need to define a few points, and this is about active constraints. So if you think of it, if you have several inequalities and one inequality is actually binding and another one is not binding, then it's not active and it will not have any influence on the local topology of your set. So we define actually the active constraints to be those which are equal at a point, with equal to 0. Yeah? So an active constraint, so active inequality so what do we call an active inequality constraint? So at a point x star, which is a feasible point, we say that hi of x star is active if and only if hi at x star is equal to 0. So if we are actually touching the constraint, that means it does not hold strictly, but it holds just with equality, then we say this constraint is active. Otherwise, we call it otherwise. Otherwise, we call it inactive. Of course, please note that we define it only for feasible points. So you are at a feasible point, and then you have this definition, and then we define the active set. The active set is actually an index set. I call it A, curly A of x star. Can be of any x, but I give it a star to make sure we mean a particular point now. And this active set is actually a subset of the set of inequalities That means of the indices of all our inequalities H, which can go from 1 to Q. And it's the collection that contains the indices of the active constraints. Just want to give you one little example. Very simple one, but just for fun. So if we have two inequalities, H1, x, which is 1 minus x1 squared minus x2 squared. So that's actually this circle. And it should be R positive, so sorry, I make it plus. Oh, it was okay. Right. And then this excludes all points which are at the outside. And maybe I add another constraint that excludes all points here, which is actually the constraint that says that some function, namely x1, should be positive. So this would be a simple setting, and now I would like to ask you a few questions just to train you. What is the active set at this point? Let's say this is point A, or I call it XA. So what's the active point at XA? And great. What is the active set at this point? XB. Okay. What would be the active set at this point? Sorry? It's not really defined. It's not a feasible point, so we will not. It's not defined here. Just not defined. It's only defined for points which are in the feasible set, in principle. So this one we will not regard. We can look at this point here, maybe. Okay, so I think we are all on board. This concept is simple, right? But now we need to define linear independence constraint qualification in order to be able to make a connection between the tangent cone and the linearized feasible cone. So let me define these two things for inequalities. Maybe I start with the linearized feasible cone, because that was an interesting object. And if you think, what would be, for example, at this point, the possible directions, they move in all directions, right? So that's easy. At this point, you would probably have a division line here, and you say everything in this direction is the tangent directions, right? So we could actually linearize that constraint, but that was only one of the two constraints. And at this point, we could actually say, oh, it's these directions that are possible. And that is based on the linearization of both of these constraints. So please note that at this point, none of the constraints enters, and at this point, only the constraint number 1 enters, while the constraint number 2 is completely irrelevant for the local topology here. So we will actually use the active set to define the linearized feasible cone, and we define it to be the set of all directions P in Rn, which have the property that, so it's actually at some feasible point. So it's, again, something we only define at feasible points. But at these feasible points, it is the set of directions which will not change the equality constraints. So they will actually satisfy the equality constraints with equality, even in the linearized fashion. But also, what we need to require is that for each of the active inequalities, the gradient, the product of this nabla H with P should be inside the feasible set. That means it should be leading upwards, because if it would go down, it would actually start to violate the constraint. But this is only needed for the active constraints, for I element in the active set. And that concludes the definition of the set. So let me just go at one example here, the same example. And we call this point at xb and xb. I would suggest we make, let's maybe make this a 2. It would be a bit easier. Then we could have here the point 1, 1. Fine. I don't need to get strange numbers. So what will be the linearized feasible cone here? xb, the set of all p, so that, so what is the active set? It was just 1. Is there any equality constraints? No, there are no equality constraints in this problem. So this part is not there, but then it will be just this thing. So what is the h1, the gradient of h1? It will be, just looking at this formula, minus 2x1 and minus 2x2. So now it should be the set where h1 at xb nabla p is bigger than 0. And okay, if we can evaluate that, it will be actually, if we say it at xb, it will have the value minus 2 and minus 2. So this will be the set of all p element in R2, so that minus 2 and minus 2 transpose p are bigger than 0, or what we could equally say is actually that, this is enough actually. So it's all the p's which are forming a positive with minus 2 and minus 2. So this is the vector minus 2 and minus 2. It's pointing in this direction. And all the vectors which have a positive scalar product with it are the vectors which are in this linearized feasible cone. And you get intuitively the picture again. This seems to be a good proxy for the tangent cone. So we should be happy. And indeed, we can be happy, but only if this linear independence constraint qualification holds that we already discussed for equality constraint problems. But how do we define it for this case? And you can already guess. So we have in this linearized feasible cone, everything that matters are the active constraints. The others, they are far away, so they don't matter. And so LICQ will also be only based on the active constraints. So the constraint qualification LICQ, linear independence constraint qualification, will now, so that's a definition. This holds at some point x star. It should be a feasible point if and only if the vectors which you get from all the equality constraints, nabla g1 at x star up to nabla gm of x star, so these are all the equality constraint gradients, and then h I of x star with I element in the active set at x star. If all, so it should be of course nabla h, so this gradient, if all these vectors are linearly independent. So that's all we need. So before we didn't have inequalities, so we had only these things that should be linearly independent. Now we take those that are still needed for the active inequalities in addition. So why did we define all this? Because now we can actually make a statement that is exactly the same as what we had before and what we have proven for the equality constraint case. And the statement is a little theorem that says at any point x star which is feasible, hold two things. First one is that the tangent, the linearized feasible cone is actually a superset of the tangent cone. So the tangent cone will be contained in the linearized feasible cone. And if LICQ holds, then they are equal. The tangent cone is equal to the linearized feasible cone. And the proof is, of course, slightly different than before, but now we have inequalities in addition. But I don't want to repeat it because it's very much similar to what we did before. What I want to do instead is I want to go through a few examples to show that for inequalities things can be also different. I mean, these two things can be different. We looked at it already for the equality constraint case, right? But let me just give you some nasty examples also here where they are not the same. So I want to give you one example for t omega at x star is not equal to linearized feasible cone of x star. And the examples that we could start with, one example is maybe this one where we have two inequalities of this form, and we will let me just start with it. So we could have here something like could be something like x. So I try to formulate it. So everything outside is feasible, and so if I have this situation here, this is a bad example. I think I wanted to invent another one. Or maybe it's not so bad. I can illustrate everything you want at this example. So it's a non-convex example, so I have, and I want to make it a bit more interesting by just having the possibility of over these curves to be actually intersecting. So I take x to the power of 3 in this direction, so here's x1 and here's x2, and I construct it so that everything above this curve is feasible. That means x1 is bigger than x2 to the power of 3. That's this curve. No, it's actually the minus sign, right? Bigger than minus x2 to the power of 3. No, because it's, you agree that this is like the things that are above in this direction out of this curve. And then I have another constraint which says that x1 should be smaller than this curve, and that curve is x2 to the power of 3. Just to have two nasty constraints. They don't look so nasty, but now I can reorder things. So I will actually say h1 of x will be given by everything here, so it will be x1 plus x2 to the power of 3, and h2. So I put everything on the positive side, it will be minus x1 plus x2 to the power of 3, and then I think I made something wrong.
x1 should be bigger or equal to x2 to the power of 3, shouldn't it?
Here you mean? Yeah, but I wanted to, maybe I should just plot what I wanted to illustrate. So this would be h1, and the other one, this should be, so let me just make it clean again. I mean the curve, this is x2, this is x1, so x2, if it's positive, then I have this thing. So with negative, I have this thing. And then x1 should be bigger than that. So that constraint, I think, is what I wanted. And here I want now that the x1 is smaller. Sorry, this is x2, right? This is x1. This is the curve x2 to the power of 3, and then x1 should be below that curve. Okay? So maybe it is all okay. Now I bring this to that side, and then I have a plus here, and I bring that to that side, and I have a plus here as well. Okay, yeah?
If you take the point 2, 0, then h1 is equal, but you are on the wrong side of the first image.
Sorry, if I check what?
The point 2, 0, with the 2 to the left.
Yeah, 2.
And so h1 is
Yeah.
2.
Yes, exactly.
But you're on the wrong side of the image, right? You can just on the left side, not on the right side.
So I think that now here h1 should be positive number, right? And it is positive, isn't it?
Yes, but you said you want to be on the left side of the curve.
No, this is always the forbidden part. Yeah, so the stripes in my plots are always the forbidden side. Yeah. So I want to just have the intersection of these two constraints, and for me, at the moment, it looks like this is what I want. And so maybe I just continue. Or if you all, or did you any? I mean, these two constraints. This is this, right? That is x1 is smaller than x2 to the power of 3. I think that makes sense also. So probably they are right, and then I bring this x1 to that side, and then it gets with a minus side. Okay, so then I have these two constraints. It looked wrong for a moment for me, but it's probably right. Okay. Now we could look at different points, and of course the interesting and nasty point, and that's why I constructed that example, would be that point, right? So let's regard x1 or x star being 0 and 0. What will be now our two gradients? I mean, first of all, what's the active set at this point? It is, of course, consisting of both these constraints. That will be 1 and 2. And now we can compute the two gradients of these active constraints. The gradient nabla h1, what is it? It is actually 1, and then 3 times x2 squared. And nabla h2 at any point x would be given by minus 1 from this thing and 3x2 squared. If we evaluate them at the point 0, 0, then this gives 1 and 0 and minus 1 and 0. So we see that nabla h1 at x star is equal 1, 0. The other is equal to minus 1 and 0. And so you see they are not linearly independent. No LICQ, because they are linearly dependent. And that means that it could be one of the cases where this theorem doesn't say they are equal. So we don't know if they are equal or not. So let's try to look at what is the linearized feasible cone. That's the easier object. So this thing, what is it? It's still defined like it was. We can always define it. It will be 1, 0, transpose this gradient times p bigger than 0. And then the other thing is minus 1, 0, transpose p bigger than 0. And basically what does it say? It says the first component of p should be bigger than 0. That's what this says. And this says this first component of p minus should be bigger than 0. And that means that it should be equal to 0. So it's actually the same as the set of all. Yeah, maybe I could directly write it like it's 0, p2. And p2 is can be anything in R. Yeah, so that's a simple set to draw, and it consists of all this space. So that's the linearized feasible cone. What will be the tangent cone at this point? the set of all vectors p, which are tangent vectors at this point. But in which direction can we move at this point? We can actually only move in that direction. There is no other direction, because whenever we have a little slope, then we will already get into either this constraint or that constraint. So our tangent cone will be actually the set of all, it's half of that set actually. So it's difficult to write it, but I can just say it's like P2, and P2 should be positive. That's it. This is not from a formula, but from looking at it and translating it back into a formula. But what we see immediately is that here, indeed, the real tangent cone is a subset of the linearized feasible cone. That's true. And so the theorem is true, because LICQ doesn't hold, the second part doesn't apply. I could actually use similar examples to show you all other possibilities that are possible. So I want to make another example. So this is, so to say, case. Okay, it's just an illustration. So it's all compatible, of course, with this theorem. This theorem is true, so I don't prove anything by examples. I just want to illustrate it. But I want to illustrate a case where LICQ does not hold, but these things are still the same. So we could also have a case where our constraints h1 of x are given by x1, and then here I don't take the cube, but just the square. And if I take the square here, and h1 of x is given by minus x2 plus x2 square, how will this look like now? It will look like this, where I have, so this should be bigger than 0 and this should be bigger than 0, always keeping that in mind. So the first constraint says I want to be above, not above, but right of that line. Yeah? So that's, and the other one says that x1 should be smaller than x and than this parabola. So I have this setting. Yeah, so I could have this situation where I have now my this point is feasible, but what will be the linearized feasible cone? It will be the same, because the gradients are the same here anyway, but the tangent cone will be also extended in both directions. So here, for this example, we will have that the tangent cone at x star is equal to the linearized feasible cone at x star, which is just the set of 0, P2, and P2 is element in R. So you can also have this, but still LICQ is of course not satisfied, because it's, the gradients are still pointing in this and in this direction, so they are just linearly independent. Yeah, so the point is, LICQ is not a necessary condition for these things to be equal, it's just a sufficient condition. Yeah? So remark, just to not forget it, LICQ is sufficient but not necessary for T omega at x star equals f of x star to hold. And then just a remark for people that are interested in literature or nice names. There's a name. If this condition holds, then sometimes people say the other D constraint qualification holds. Yeah? T omega at x star equals f omega of x star is sometimes called A bar D constraint qualification. But it's something that's not easy to check. Just so that we know this name. But for us, the bottom line is the same theorem as before holds. The tangent cone is always contained in this linearized feasible cone. The linearized feasible cone can be too big, but if LICQ holds, or some other constraint qualifications, then the two are equal. And because they are equal, we can now translate our little theorem. Where is it? This theorem variant that we have here. We can actually translate it to a very simple thing, namely to the second variant that we had already before, also in the equality constraint case. And so we can just have a theorem which is now variant 2. So we are starting to approach ourselves again to the to something more computational. If x is a local minimizer, so let's assume if x is a local minimizer and LICQ holds at this point, then okay, x star is feasible, clear. And second is, because now the linearized feasible cone and the tangent cone are the same, I could also say for all p in the tangent cone, this is in the linearized feasible cone, we have that p transpose nabla f at x star must be in uphill direction. That's it. We could also translate this other thing just alternatively. I just want to rephrase it. To prime. I could also say it's not true that there exists a p in the feasible cone which is going down. Right? For all p in the feasible cone it's going up, so I could also say it's not true that there exists a p. Just say it is not true that there exists p in this linearized feasible cone with p transpose nabla f of x star smaller than 0. It's just a different way to express the same fact. And this is the thing where we will build on. Because now we want to use, like before, we had these Lagrange multipliers, and at some point we could actually rephrase this necessary condition for optimality with an existence. So here we do something, it's not true, but what we would like to have is there exists some multiplier so that something is true. And then we can have a much more computational way to hold it. And we will see that this is slightly more complicated for inequalities, and we will go through it in a minute, or not in a minute actually. I think we will do it possibly after the break, because I think it might make more sense to do it after the break, yeah. Are there questions until now? Maybe just to help digesting the stuff that we did until now. So we just came into, nothing really big happened, I should say. If you were familiar with the equality constraint optimality conditions, we just said something, we stated something obvious, the variant 1. Then we said, okay, if we would have this LICQ condition, which is now involving also the constraints of the active inequalities, then the tangent cone and the feasible cone are the same. And then at the very end, we just reformulated this thing with a slight negation into something which is the same thing but differently stated. And this is only to prepare you to some statement that is called Farkas lemma and that I want to introduce after the break. Or do you want to have it now? It would take 10 minutes. After the break? Yeah? Okay. So let's do it after the break. And we do a 7-minute break. Is that okay? It's sunny. Maybe we can stop a bit earlier later then. Okay, are you ready to continue? If so, then I would like to continue exactly where we stopped the last hour. We just arrived at one form of theorem, and I summarized it like this. And I want to replace the second condition. And in order to massage this a bit further, I want to make some shorthands, and then state a general statement, and then find a more elegant or more powerful expression for this one, which is completely equivalent. But let me just first say a few shorthands, yeah? So that it will allow us to understand the lemma that comes better. So the first shorthand is that we will just say C is equal to nabla f of x star. So we will call it C. We will also call the gradient of our equality constraints. This matrix we will call H. So please recall that this is the matrix that contains all gradients transposed. So this was, before I think we called it the Jacobian J of G, but now I call it big G. And then I will also introduce a matrix which I call H, which is containing the active inequalities in some arbitrary order, I should say. This is difficult to write down notationally, but the meaning should be okay for I element in the active set at x star. So this matrix contains all the active inequality constraints, and then actually I could write with this shorthand the linearized feasible cone is the collection of all p, so that G times p is equal to 0 and H times p is bigger than 0. So this is a shorthand to write down the linearized feasible cone. So this is saying that all the equality gradients are equal to 0, and that means that all the active inequality constraint gradients multiplied with p are bigger than 0. Do you agree? Okay. So this is just some shorthands, and I want to use them, and actually not exactly to use these shorthands, but it's good to keep in mind what they mean. Because I will now use the symbols G, H, and C with the right dimensions in a lemma that is actually much more general than what we need it for, but we will need it for this one. So note that this second, maybe I should, I first state the lemma. And that is a lemma that is called Farkas lemma to Farkas. And this lemma regards any matrices that I just call generally, but I call them now G, element in Rn. Now it's Rm times n, right? So that the dimensions are right. And H, element in some arbitrary dimensions, I call it actually Q times n. We should say that Q is not exactly the same Q as before, because it's only the active ones now, right? And I have a vector C in Rn. And then whenever I have these things, then I can make a strong statement about two things that cannot be true at the same time. And so it's called a theorem of the alternative sometimes, because it's just something that is stated in form of alternatives. So for any two matrices, only one of the following is true. And to be sure that the statement is it comes over, I write here either something or the other thing. And so what it says is that either, and now it makes a relation with lambdas and mu's, and we will prove it afterwards, but either there exist lambda in Rm, and mu in Rq with mu positive and C being a linear combination of the rows of G and the rows of H, each of them weighted with mu. So this is either true or some other thing is true, or there exists a P in Rn which has the property that G times P is equal to 0, that H times P is bigger than 0, and C transpose P is smaller than 0. So it's two things which seem to have not much to do with each other. But this is called Farkas lemma. It says that one of the two things is true, so either there exist multipliers lambda and mu that actually give together the gradient C, or there exists a P, you could translate it in the linearized feasible cone, that is a descent direction. So if either of the two is true, and one of the two is always true, the other is always false, then actually this thing is the negation of that thing, that there exists a P, right? So actually then so then the theorem, I will prove it later, prove in a minute, later. But after we have stated this, I could actually make it useful, and then I can just say a theorem which is the first order necessary conditions invariant 3. And it just says if x star is a local minimum and LICQ holds, then first of all x must be feasible, but that means basically that g of x star is equal to 0 and h of x star is bigger than 0. That's what it says. All right, the first part. I just write it a bit longer. And the second thing is now using this. There exist lambda and mu, with mu positive, and so that the gradient of f of x star is equal to the gradient of g of x star times lambda plus, and now I maybe write it better this way, I element in the active set at x star nabla h I at x star times mu I is equal to the gradient. So that's just a translation of this statement from above. So in order to say already where it is good for, so this would be a variant of this. So this mu would be in the dimension of the active constraints at the moment. And this would be exactly the same as this statement if Farkas lemma is true. So that's what it is good for, but now let me try to sketch why this lemma of Farkas is true. It's not, it sounds a bit strange. Maybe I should first I could actually do two things. I can first prove it, or I can first illustrate it for the special case that we don't have inequalities, because then it gets easier. Should I do it first without inequalities, just to get the notation a bit easier to help to digest it? So it's a corollary of Farkas lemma. For Q0, so there is no H matrix, and then it says either, what does it say? Either there exists lambda, I leave the element away, that's clear, right? Such that C is equal to G transpose lambda, or there exists a P so that G times P is equal to 0 and C transpose P is, okay, smaller than 0. So this is the simplest variant of Farkas lemma, and you see that this is actually something that we used already before. Yeah, so we said that C, we could also use this because this is symmetric in this case. We could also just have inequality here, right? So we could say that C is not orthogonal to the null space of G, means this can be either the case, it's not orthogonal, or C is a superposition of the rows of G. That's what we used before. You remember that with the singular value decomposition, we had a very quick proof of it. We proved that already. We didn't state it in another form, but Farkas lemma is actually a way to state the same thing, but extend it also to inequalities. Yeah, so this is as before. So this was a corollary of Farkas lemma, so to help digesting it a bit. But I still want to prove it, because it's not too difficult actually. And I think it's nice to prove it once, to get a feeling of what it means. And the crucial thing is that we introduce a set, so the proof of Farkas lemma. And what we will do is we introduce a set which I call S. And this set consists of all directions, it's all vectors actually, which are the vectors G transpose lambda plus H transpose mu, where lambda is just any vector in Rm, and mu is a vector in Rq, but mu is also positive for each component. So this is a set. It's actually a conic set, so you could imagine the set to be something, maybe I illustrate it here. So S could be something, if we would have only inequalities, it would look like this. Yeah, so it's, yeah. This set could be S. Yeah, so imagine that you would have only positive, only inequalities, then it would just be all the rays that are pointing, and these are actually the gradients nabla h I at x. Sorry. This is now already with the interpretation that I have in mind, but it's for Farkas lemma we don't need them. Yeah, right. So these are the rows. Rows of H. So the rows of H point in directions, and if you do some positive linear combinations, you get the set S. And if you have also equalities, then some of these directions might actually get, yeah, let's say there is a third dimension, then we could have something infinite in this direction. So in both directions. Just to get you an illustration. So this set S is called a convex cone. It's relatively easy to check that it would be a convex set, and it's a cone, so it's a convex cone, but that doesn't really matter. The main point is that it's convex. And so now we define another point, and the point is just C. C. And this point C, something that I can locate somewhere. This is, by the way, the origin. Anyway, I can have a C. And now I can make two statements, and this is completely easy. I can say either this point C is in S or it's not in S. That's clear, right? So if it's actually, let me start in the right order. So either C is element of S or C is not element of S. So C element in S is obviously the first statement of our of Farkas lemma, right? Because if S is inside this thing, then there exists some lambda and mu, so that C is actually given by this linear combination, and then we have the first. So that's relatively easy. But now let's translate this into what we have here. So if C is not in S, that's this situation here. And there's some theorem which we will not prove now, but which I think is very intuitive, and that is called the separating hyperplane theorem. And that says if you have two convex sets, this is a point, this is a set, but the point is also a set, it's also convex, just a point. If you have two convex sets, there is a plane in the space that you can just put between them. For example, this one, that that ensures that one of the sets is on one side of this hyperplane, and the other side, the other set is on the other side. And we will actually separate them. I mean, there is some definition what we put on one side. I think we will use the separating hyperplane theorem. So the thing that is intuitive, but we don't prove. Separating hyperplane theorem. And what does it state? If C is not element in S, then there exists some hyperplane, and this hyperplane we will actually denote with a vector P. That's a bit funny, but that's actually the intuition, because a hyperplane will be defined by a vector P. And now let me just think of, I think we make it like that. So we introduce a vector P, which is orthogonal to this plane, and we say that C is not in S, then exists a P, so that for all Y in S holds that P transpose Y is bigger than 0, and P transpose C is smaller than 0. So here you have this the positive product, so on that side. On this side you have the negative scalar product. So P with any vector Y, this is element in this set, will give a positive number, and with the C it will give a negative number. And as long as the C is not in that set, there exists such a plane. I mean, if the C would be very close here, then you would tilt it a bit, but it would still exist. Yeah? So you can intuitively see that such a separating hyperplane will always exist. And I call it already P, but basically this P is just the orthogonal vector that defines a hyperplane. Yeah? So P times Y equals 0 is this set. Yeah? So that's the separating hyperplane. Maybe I draw it in yellow. So, and on the plus side, doesn't matter actually, here's the P. Okay, and so this is even in both directions, because if such a P exists, then also the S cannot be in the set. So this is actually equivalent. So we can translate this thing. So we go on with this part, and we say this is actually equivalent with saying there exists a P, so that, let's just state it, for all Y in S, for all, and now I can maybe do it first of all, for all Y and S, we have that P transpose Y is bigger than 0, and C transpose P is smaller than 0. It looks already a bit like that, but it doesn't really exactly look like that. So let's translate this. What does it mean Y element in S? Y element in S means that it has that there is a lambda and a mu that have this property. So we can actually say this one I just put to the front because it's so easy. So I just copy it. But then this thing is there exists a P. This one I should have to the front. Exists a P, so that C transpose P is smaller than 0. And now let's now say for all Y, but actually this means for all lambda and mu, where mu is positive. So I write it like this. So all arbitrary lambda, but the mu's should be positive. This thing should hold. And then it basically means P transpose, and then the Y I write directly like it was. It's G transpose lambda plus H transpose mu. This thing should be positive for all lambda and for all mu. And now I can also transpose this statement, and I will just realize one thing. If you have the vector GP, and you multiply it with all lambda transpose, and here you have the vector HP, and I multiply it with all positive mu, and this whole thing will always be positive, whatever I choose for lambda and mu. So that's what this says, right? So this is in brackets. What does this mean? If lambda can take any value, I mean, mu can always take also 0. So if lambda can take any value, then this means actually that GP must be 0. And on the other hand, this lambda could also be set to 0, because it should hold for all. Mu can only have positive values. If this should always be positive, this can only hold true if all the components of HP of this vector are positive. So actually, with these brackets, I can continue to make the statement that there exists a P, so that C transpose P is smaller than 0, and for all lambda mu this holds, but actually this means basically that GP is equal to 0 and HP is bigger than 0 for every component. And then we have it. Because either C is in the set or C is not in the set, but C not being in the set means there exists a separating hyperplane in form of this vector P, so that it separates the point C and the set S. And this separation was then translated into this equality that the point P should satisfy. And that is exactly the statement that we had here at the top of the lemma of Farkas. So it's a bit abstract, and it's a bit mind stretching, I would say, but it's done. Okay? So the funny thing is that we were moving into a space which was consisting of all these linear combinations of the rows of our matrices, so the set S, and that was a crucial step to separate S from the point C. So we looked at the gradient as a point in a space, and we separated it. And P was not a feasible direction or something, but it was just a separating hyperplane. So it's a very strange way of thinking, but a very powerful one, because now we have proven our lemma of Farkas. And with the lemma of Farkas, we have now a way to formulate our first order necessary optimality conditions in an existence way. So the first time we have something that is only requiring existence. Like before, that was computationally nice. So we are here at the top, where we say now we can say there exists lambda and mu, so that the gradient of the objective is a linear combination of the gradients of our constraints. Actually only of the equalities and the active inequalities. I will now continue on that blackboard, so contrary to our usual custom. So we continue on that side. And I want to prove a theorem which is now actually already, it's a third variant, so first order necessary conditions. This was variant 3, then it's variant 4 already. So it's a long route, but this is called already the Karush-Kuhn-Tucker. Conditions, or first order necessary optimality conditions. And this says actually the same thing, but in slightly different. If x star is a local minimizer and LICQ holds at x star, then there exist multipliers. And I now refer to the original problem. So then there exist lambda star in Rm and mu star in Rq, and I refer to the full space now, all the inequalities, so that the following conditions hold. And now I will state a collection of conditions which will be actually equivalent to what we have here at the top level here. And what will be these conditions? I will maybe reorder them slightly, but this is actually not a big problem. So I will actually write nabla f of x star minus nabla g of x star times lambda star minus nabla h x star, and now I refer, this is actually the full matrix, all the components of h times mu star. This should be equal to 0. The equalities x star should be equal to 0. The inequalities x should be positive, all of them. This is clear, that's just feasibility. This is somehow what we just stated, namely this nabla f is a linear combination of these and these things, but there are some mu's which I have reintroduced which were not there before, because the mu's for the inactive constraints. And now I want to actually exclude, first of all, that the mu's get negative, because I said mu must be positive. There must be positive multipliers. And then I will make actually sure that the mu's which are corresponding to the inactive constraints, that these mu's are 0. And because both of these things are are positive, I can actually require that the product of x star with mu I should be 0 for I from 1 to q. And that means if there was a positive, that means an inactive constraint, then automatically this mu will be set to 0, and it will not contribute here. So, the proof is use the variant 3. So we see this here already, but here we had only the active multipliers. But set mu I star equal to 0 for hi of x star bigger than 0. So for the inactive constraints. And then we can see that this will actually, so we know already, and then maybe we end use that nabla h of x star times mu some vector here, is actually the same as the sum over the gradients, of all the inequality constraints times the multipliers, where I first sum over the active set, and then I could also sum over all the other constraints where I is not element in the active set. And so I can actually, this product here is actually a linear combination of all the gradients, and I take first the gradients which are from the active set, and then I take all the gradients from the inactive set. And because I've set all these things here to 0, I will actually have this thing, and that was exactly what I had here above. So Farkas lemma only refers to the active constraints, and but by setting all the other multipliers to 0, I will still be able to make this thing true. Also, Farkas lemma guarantees that this mu is positive, and 0 is also non-zero. So, sorry, it's non-negative, right? So 0 also satisfied it. So all the components of mu, they will be positive. Some of them will be 0. And here, if this is positive, then, and I choose this 0, then this still will be 0. If this is active, then this is 0, and then this is 0 anyway. So all these conditions will be satisfied. It's just something that we can derive from the thing that we had already before, as I said, by setting things before to 0. There's one different way to state it. This is component-wise, right? This is also component-wise, so maybe it's nicer to put an index I here, and then have this index I applied to all these three things together. And why do I do it? Because I have an H and a mu, and I have a product of the two. And these three things together, they are something that I want you to have a notion about. And I want to illustrate what these three conditions together mean. They actually say that if you have an hi of x star here and a mu I star here for any I element in 1 up to q, you can make this plot, and then these three conditions together, they make sure that you are either here or here. I mean, the product of the two must be 0. That already makes sure that you are on this line and on this line. Everything, one of the two must be 0, or both at this point. But then both must be positive, so that excludes the negative part of the cross, and that means only this or this part can be true. So these are the points which satisfy these last three conditions. Yeah. So this is actually where the mu I star is positive, and the so the h I x star is positive, and the product of the two mu I x star times h I x star is equal to 0. And these three conditions together are called complementarity conditions. So the last three of these KKT conditions are complementarity conditions, and they are particularly interesting, and they are new, and they are specific to the inequalities. While this part we knew already, that's the same that we had for equalities. Yeah, and this condition we also knew from equalities, right? But here we just have the addition of the gradient of the constraints to the Lagrangian, and we have the complementarity conditions, and that is different to what we had before. So maybe I do the same thing that we did here for the corollary, just to make you relax a moment. So if you look at these, and if you would have, so for q equals 0, so if there would be no inequality, then of course this reduces to what we know. We get nabla f minus nabla g times lambda equals 0, and g of x equals 0. That's what we had already before. Are you on board? Not completely? Okay. I think it might make sense to do a little example. Is that okay? Maybe that helps a bit. And maybe I do exactly the example that we do here in the script to have something that you can follow afterwards. So example, actually here I will do m equals 0, so there's no equality constraint, and I have q equals to 2, and n is also 2. So I have a two-dimensional example like always, because then I can plot so nicely on the blackboard. And my example is this problem where I say I minimize x, my function is 0 minus 1 transpose x, subject to two constraints, and my two constraints are now x1 square plus x2 square minus 1. And the other constraint is minus x2 minus 2 square minus x1 square plus 4. And this whole vector should be bigger than 0. So that's the way I write it. Maybe before I continue to compute numbers, I should illustrate it so that we don't get lost in these numbers. So x1 square plus x2 square should be bigger than 1 is what this says. So it's actually saying that here's x1, here's x2. So the first constraint says that we should be outside the unit circle, so the inside is forbidden. Okay. What does the second constraint say? It says basically that our distance from the point 0 and minus and 2 should be smaller than 2, because it's a squared radius. So which point do we have here? So we subtract from x2 the point 2, so that is here. So what it says is that we want to be inside a circle which is actually given by this thing. So that's a circle around that point. And we are this situation. It's a very funny thing. So what do we want to minimize? We want to minimize the negative of it's a completely crazy example. Unfortunately, I just realized that our okay, so I plotted it a bit wrong. Not wrong, but I think you should just imagine to make this circle around. And because our objective is actually to maximize x2, our optimal point will be up here. So I drew it a bit different. Maybe I should draw it a bit smaller. So this is this thing. And then I have the big circle here. And here is actually my point. So that will be x star, and it will be 0 and 4. Yeah, I don't know why I added this stupid inequality here. Okay, it's bad when you do old examples, but anyway, okay. So let us just go through it. So what is the active set at that point? Maybe I go on here. Exercise, what is the active set? I have two constraints. This one is H1, this is H2. 2. It's the second one which is active here. I mean, we're just at this point up there. And now I can compute the gradients at this thing. So what is the gradient of the objective? It is actually identical to this value because it's a linear objective. What is the gradient of the active constraint? H2. At x star, it will be given by the derivative of this thing, which is minus 2x1 star, and here we have minus 2 and then x2 star minus 2. But now, because x star has the value 0 and 4, that will be 0, and it will be 4 minus 2 is 4, and then it's minus 4. Wonderful. Okay, great. And now I want to see if I can make true that the KKT conditions are satisfied. So what will be the KKT conditions? So they say there exists a lambda. Actually, there exists a mu1 star and a mu2 star. So that the following things should be satisfied. So this nabla f, I just make it small, is equal to nabla h1 times mu1 minus nabla h2 times mu2. But this should be equal to 0. That's the first condition. And now I can write it in in numbers. So the numbers are 0, minus 1, minus the gradient of the first constraint. I will actually multiply it with 0 anyway, so I'm not interested in it, but I write it for a moment. And then minus, here I have minus 0 and minus 4 times mu 2 star should be equal to 0. That's the first condition. The second condition is actually g equals 0. That's not there. Yeah, so this g is not there. But then what are the other conditions? It says actually h1 of x star should be bigger than 0, and h2 of x star should be bigger than 0. I could formulate these things if you want, but I could also just copy these lines, so that's a bit boring, but maybe let's do it once to be complete. So that's what this says, and this says x2 minus 2 squared plus x1 squared minus, plus minus plus 4 bigger than 0. So these were the less interesting conditions, but now we also say that the multipliers must be positive. So actually mu1 star should be positive and mu2 star should be positive. So these things are, anyway, they are the same on the right with numbers or with formulas. And the last condition says that the product of mu1 star and h1 of x star should be equal to 0, and the same should also hold for mu2 star times h2 of x star. So that's the last, these complementarity conditions. And now let's see if we can make these satisfied. And of course, I said already that the mu1, the multiplier of our inactive constraint, the one where the constraint is anyway positive, so this constraint is inactive. So this multiplier we will set to 0. Mu1 star will set to 0 anyway. So then we will have these two numbers, and these two numbers, they should match. Then we immediately see that we should choose mu2 to be 1/4, right? Because then with minus 4 it gets the same as minus 1. So we set mu2 star to be 1/4. We can check that this condition is satisfied. So then the first condition is satisfied. This condition is satisfied anyway. That was inactive, the constraint, so that was even strictly positive, right? This one was satisfied with equality, so that's also something we knew already from our point that we want to check, 0 and 4. The two multipliers are positive or non-zero, non-negative, so mu1 is positive, mu2 is positive, and the products are also by construction 0. This constraint was positive, but the multiplier was 0. Here the multiplier was non-zero, but the constraint was active and 0. So the products are also 0. So these things are all satisfied, and so we see that the point x star satisfies the so-called KKT conditions. That means it's a candidate for a local minimum. It doesn't mean that it is a local minimum, but it's a point that satisfies the necessary conditions. Okay. These are the KKT conditions. Do you want a quick stop, or do you want to have one more delightful bit, which takes 8 minutes to prove and discuss? Actually, I think we should stop because the breakboard is full anyway. Okay, and it's also better to stop with a not too full stomach of mathematical things, and to have still some space left for Christmas dishes. Okay, so I wish you a wonderful time, and I'm looking forward to see you actually on Friday, the 8th of January. It's a wonderful date. We will see back at that time. I should also make some announcements. So there will be no exercise group tomorrow. We updated some things in the internet, and I think Dimitri sent out an email to you, I hope. Yes, he did. And we will have this Friday lecture next January, but afterwards there will be no lectures on Fridays anymore. On Fridays there will be time for projects. So the projects are really an integral and important part of this, and so we reserve time for it. And only the last lecture of the last Friday will be again, so to say, a lecture, but it will be given by you. So that's where you will present your lectures. And on Tuesdays we will continue to digest a few more things that we still want to cover about inequality constraint optimization and a few details that I think are really important and interesting for you to know. But the focus will shift a bit away from the lectures from now on and much more to the projects in January. Okay, so thanks a lot and happy Christmas and a good start into 2016. Thank you.